Let's now proceed to the class of Lebesgue integrable functions. So for the definition, let's start with a measurable function f. So now we do not assume that f is non-negative. So first, let us recall the definition for the positive and negative parts of your function f. So the positive part of f is defined to be the max between f and 0. And this is assumed to be pointwise or defined to be pointwise. And f is the max of negative f and 0. Or this is the negative mean, the minimum between f and 0. That's the positive part and that's the negative part. Then one can show that f is the difference of the positive and negative parts, and these are also measurable and they are non-negative. So we say that f is Lebesgue integrable if the Lebesgue integral for the positive and negative parts viewed as non-negative measurable functions are finite. So, and in this case, we define the Lebesgue integral of f and taking note this identity here. Okay, so we define the Lebesgue integral of f as the difference of the Lebesgue integrals of the positive and negative parts. So here, the integrals on the right-hand side is the Lebesgue integral for non-negative measurable functions. So for Lebesgue integrable functions, the Lebesgue integral is defined in this way. So as long as the positive and negative parts are finite. Okay, so take note that this is consistent with the Lebesgue integral for non-negative measurable functions. So that is, if f is non-negative and measurable, then its Lebesgue integral is the same as the Lebesgue integral for when f is viewed as a non-negative measurable function. This follows immediately since the positive part of f is the same as f and the negative part of f is identically 0. And you will end up with only the first term since this would be 0. So again, we have consistency of the Lebesgue integral for integrable functions and for non-negative integrable functions. Okay, of course, here we need to add the condition that the right-hand side is finite. In order for both sides of this to be finite. So extending this definition for complex valued functions. Okay, so let's consider a function f, which is complex valued. Okay, so here we assign the Borel sigma algebra on C to be the Borel sigma algebra on R squared. So we give the topology of the Euclidean plane to the complex plane. So open sets in R squared are precisely the open sets in the complex plane. Here we identify, let's say, a complex number x plus iy with the ordered pair xy of real numbers. Okay, so this function is called Lebesgue integrable if the real part and the imaginary part are Lebesgue integrable. So take note that the real and imaginary parts are now measurable functions with respect to real valued measurable functions. And in this case, we define the Lebesgue integral of this complex valued function to be the complex number obtained as follows. So the real part is the Lebesgue integral of the real part, and the imaginary part is the Lebesgue integral of the imaginary part. So again, the right-hand side here are integrals for real valued functions, and the left-hand side is the notation for the Lebesgue integral for complex valued functions. Okay, so in order to accommodate or in order for our statements to accommodate both the extended real valued case and the complex valued case, we introduce the notation K. This is either R bar, or a C, or K is R or C, and K bar to be either R bar or C. And likewise, so we define the set of all Lebesgue integrable functions from, let's say, a measure space x sigma mu to R, or I should say K bar, to the corresponding Borel set by L1, the measure space, and then the corresponding measurable space for the range. Since this is a bit cumbersome, or simply we denote it by L1 x mu. If the sigma algebra is clear and the range of values is clear in the context. Okay. So our first observation is the following theorem. First, f is integrable if and only if the absolute value or the modulus in the case of complex valued functions, is integrable. Furthermore, if f is integrable and this is real valued, then the Lebesgue integral of the absolute value is the sum of the Lebesgue integral of the negative part, or of the positive part and the negative part. Okay, so to prove this theorem, again, we need to distinguish two cases, the real case and the complex case. So for the real case, we only need to apply the following inequalities. So the positive part is bounded by the absolute value as well as the negative part. And that the absolute value is just the sum of the positive and negative parts. So I will leave the details for you to verify. The first equivalence. Okay. So take note that if f is Lebesgue integrable, then the Lebesgue integrals of f plus and f minus are finite. Therefore, the Lebesgue integral of the absolute value of f is also finite. And vice versa. If the absolute value of f is Lebesgue integrable, then the integral of the positive and negative parts are finite as well. Therefore, the function f is Lebesgue integrable by definition. And in the complex case, you can apply the following set of inequalities, wherein the absolute value of the real part is less than the modulus. The absolute value of the imaginary part is also bounded by the modulus. And the modulus of f is bounded by the sum of the absolute values of the real and imaginary part. So these inequalities will imply that f is Lebesgue integrable if and only if the real and imaginary parts are Lebesgue integrable, and use the real case. So that's the proof, or let's say the sketch of the proof. For our next theorem, well, this is similar to the case of simple functions and the case of, let's say, non-negative measurable functions. Suppose that I have f. Let us look at the complex case in general. So if you have a Lebesgue integrable function f, and I have the following representation. So f can be written as follows. So g minus h times I minus pq, where G, H, P, and Q are non-negative measurable, and they are integrable as well. Then I can use this representation to calculate the Lebesgue integral of the function f. So that would be the real part, and the imaginary part would be written in this way. So to prove this, take note that f can be written as the real part of f plus I times the imaginary part of f. And then we split this into the positive part okay, so that's for the real part, and we do this for the imaginary part as well. So this must be equal to this, and the imaginary part must be equal also to this one. So therefore, rearranging the terms, we have the following. So G plus, or I should say the real part of F plus H is the same as G plus the negative of the real part of F. And in a similar manner, we obtain the following identity. Okay, so with this, we now apply the linearity of the Lebesgue integral for non-negative measurable functions. So you will get the following equations. This will be for the real parts, and this will be for the imaginary parts. Okay, so by definition, we know that the integral of f is the sum of the Lebesgue integrals for the real and imaginary parts. And you can split, of course, the positive and negative parts for the real and imaginary parts as well. And you end up with the following equation. Okay, so from this, we can now apply these two equations, say 1 and 2, and apply 1 and 2 after rearranging the terms. Okay, so you move this term on the left and you move this term on the right. So you will get this real part here. And you do that as well for the imaginary parts. Okay, so if you can write f in this way, then you can also use this to calculate the Lebesgue integral of f. So you can think of this as a special version of the linearity for Lebesgue integrable functions. And in fact, that is what we will prove in the next theorem. So take two integrable functions, f and g, and two scalars, alpha, beta, either real or complex. Then the linear combination is also Lebesgue integrable, and the Lebesgue integral of the linear combination is the linear combination of the Lebesgue integrals. So in particular, the space of Lebesgue integrable functions is a vector space over the field K, which is the field of scalars. And again, it is enough to prove the following two identities. So first, we can pull out the scalar alpha in outside the integral, and that the integral of the sum is the sum of the integrals. Again, we will prove this in two cases. Let us first consider the real case. And take, at the moment, a non-negative scalar alpha. Then, the positive part of alpha f is the same as alpha times the positive part of f. And this is also valid for the negative parts. And therefore, the Lebesgue integral of alpha f, which is the Lebesgue integral of the positive part and the negative part, and applying the previous identity, you have this. So here we apply the definition and apply this equation here. Now, we use the linearity of the Lebesgue integral for functions in M plus, okay? And we have shown this in the previous lecture. So this is equal to alpha times the integral of f plus d mu minus alpha times the integral of f minus d mu. After factoring alpha and taking note that the difference of the integrals of f plus and f minus is the same as the integral of f d mu. So that would be the positive or the non-negative scalar case, for a negative scalar alpha, the positive and negative parts will be switched. So I have here negative alpha times f minus plus. And this is the same since alpha is negative as the absolute value of f minus plus. So based on this, the positive part of alpha f is, we know that it's the absolute value of f alpha times f minus, and its negative part is absolute value of alpha times f plus. If we factor the absolute value of alpha, d mu minus plus d mu. So we can pull out now the or apply again the linearity on m plus. But this is the absolute value of alpha times the negative of the integral of f d mu. However, since negative of the absolute value of alpha is the same as alpha, since a is negative, this is the same as alpha times the integral of f d mu. So from here, it follows that in particular, that alpha f is also integrable, since the right-hand side is finite. Okay, now for the sum, if f and g are Lebesgue integrable, then so is the positive and negative parts. And the absolute value of f plus g by the triangle inequality. And we know that this is equal to the following sum. So the integrals of all functions on the right are finite, thus the absolute value of f plus g is Lebesgue integrable. And so we know that a function is integrable if and only if its absolute value is also integrable. So the sum is also integrable. And now we can represent the sum as the difference of two non-negative measurable functions. And they are also integrable. So these two are non-negative measurable and integrable. And we know that, of course, we can use this as, or we can use this to compute the Lebesgue integral of the sum due to the independence stated a while ago. So this should be d mu minus the Lebesgue integral of f minus plus g minus d mu. Again, thanks to the linearity of the Lebesgue integral on m plus x sigma, or I should say we can now write this according to independence. We can write this as one as follows, I should say. So one integral for f plus, another integral for g plus, minus d mu minus the integral of x g minus d mu. Here, let us go back to the previous theorem. So here we applied this theorem where g is the sum of the positive parts and h is the sum of the negative parts. Okay, so based on this, we just combine these two and the other two, and you now get the integral of f plus the integral of g. Okay, so that's the case for real valued functions. For the complex case, I will leave the details for you to read on the course notes. So the basic idea is to apply or separate the real and imaginary parts respectively, and apply the real case, of course. Now, now that we have the linearity for Lebesgue integrable functions, and we apply the same strategy as before, linearity implies monotonicity. So if I have two real valued integrable functions and f is less than or equal to g, then the Lebesgue integral of f is less than or equal to the Lebesgue integral of g. So you follow the same trick as before. Now let us continue describing other properties of the Lebesgue integral. So the first one is, let's say, the continuous version or the integral version of your triangle inequality. So having a Lebesgue integrable function f, the let's say absolute value or the modulus of the Lebesgue integral is less than the Lebesgue integral of the modulus. Okay, so for the proof, let us assume without loss of generality that the integral of f, well, let us define this to be I for simplicity, to be not equal to 0. Otherwise, the inequality is trivial because the left-hand side would be 0 and the right-hand side is obviously non-negative because the absolute value or the modulus of f is a non-negative measurable function. Let us introduce a scalar alpha, which is the conjugate of I divided by its modulus. So here, the denominator is not equal to 0 by assumption. So computing the magnitude of I, this is equal to the magnitude of the, or we should say, this is alpha I. This is obtained by multiplying I here both sides and taking note that the product of the conjugate and the complex number is the modulus squared. Okay, so let us write that down. So take note that alpha I is equal to I bar times I divided by the modulus, but then the numerator is the modulus squared. So you end up with the magnitude of I. So starting, let's say, the definition of I, based on the above inequality equation, this is alpha I, and this is alpha times the integral of f. You apply here linearity to put the scalar alpha inside. Okay, and this is in the complex case the real part of alpha f and d mu plus I times the imaginary part of alpha f d mu. But take note that this is real. Okay, so therefore this would imply that this must be 0. So the imaginary part of this complex number must be 0. So we can now estimate the real part is less than the modulus. Okay, and then the product of the modulus or the modulus of the product is the same as the product of the modulus. And according to our definition, okay, the magnitude of the conjugate is the same as the magnitude of that complex number. Therefore, the magnitude of alpha is 1. And this is now the desired inequality stated by the theorem. So this is the integral version of your triangle inequality for real numbers, or for let's say even for the vector case. Next, Lebesgue integrable functions cannot have infinite values on a set with positive measure. Put in another way, if I have a Lebesgue integrable function f, then the measure of the set where f is positive or negative infinity is 0. Again, for a Lebesgue integrable function, the set of points where the function assumes the positive or negative value, positive or negative infinity, I should say, should have measure 0. So let us introduce the following sets. E sub k. So this is the set where the magnitude of f is greater than k. Obviously, this is in sigma. And similarly, we define E infinity, the set where f assumes positive or negative infinity. Again, by measurability of f, this is in sigma. So let's start with the Lebesgue integral of the absolute value or the modulus. Then, by monotonicity, since here, so you apply monotonicity and the fact that the characteristic function is less than or equal to 1. Therefore, you have this identity here or inequality here. So again, the first one is basically the monotonicity for the Lebesgue integral. And again, this is the same as, since we again apply monotonicity once more. This is k times 1 e to the k d mu. And this is a simple function, therefore the Lebesgue integral is k times the measure b sub k. Therefore, for each k, we have this. And by Lebesgue integrability, this is finite for all k. Now, if you set k to be large, then the set E sub k will be smaller. So your sequence is decreasing. And we know that the measure of the first set is finite. We can apply the continuity and also take note that E sub k decreases to E infinity. We now apply the continuity of the measure to obtain the following. So this one is the same as the measure of E infinity. And this is, well, as k goes to infinity, this one goes to 0. And that's precisely the statement of the theorem, since this is E infinity. Okay. So far, we have integration over the whole set X. We can also define integration over a measurable subset of X. So let us consider an integrable function f and a measurable set E. Then we define the Lebesgue integral over E to be the integral of f times the characteristic function of E. Take note that this is finite since obviously the magnitude of this product is less than or equal to the magnitude of f, since the characteristic function is either 0 or 1, and you apply monotonicity. And the fact that, of course, f, hence the magnitude of f is also integrable. Okay. So with this notation, we have the following observations. So let E be measurable as well as F. Now, in addition, if F is non-negative and it is Lebesgue integrable, or I should say Lebesgue integrable, and the measure of E is equal to 0, then the Lebesgue integral over E of F is 0. Also, the Lebesgue integral of the magnitude is 0 if and only if the set of points where f is not equal to 0 has measure 0. So let us look at the proof, and let me emphasize here the main strategy in proving such properties for the Lebesgue integral. So first, let's start with the characteristic function case. So here, suppose that f is this indicator function, where a is in sigma. Then the integral of f d mu, according to the definition of f and the definition of the Lebesgue integral over a set. So this is the product of the indicator functions of a and e. That is the same as the integral of the indicator function of the intersection. And of course, this is the measure of the intersection. Since the measure of E is 0 and the intersection is a subset of E, this is 0. by applying the monotonicity of your measure. So the case of characteristic function has been established. So let us extend this to the case of simple functions. So suppose f is, let's say, a linear combination of alpha k from 1 to n, k, and this is a simple function. So you apply the case of the linearity. So this would be first, let us apply the definition 1e d mu. So this is the basically the definition of the integral over a set. And here alpha k 1ak indicator of e d mu. Linearity. You apply the linearity of the Lebesgue integral, and this will be k from 1 to n alpha k integral over e of this indicator function. Since we know that the integral over e of indicator or characteristic functions is 0, so you apply here the characteristic case. So now we know that the equation here is valid for simple functions, non-negative simple functions. The next, of course, is for non-negative measurable functions. So suppose f is in m plus. So the idea is to take, well, following the definition of the Lebesgue integral for non-negative measurable functions, this is a sequence in S plus such that phi n increases to f. Again, we apply the definition of the integral over a set E. Since the indicator function is non-negative, we have the following. So this is f times the indicator function of E, and phi n 1e is a, or using this, we apply the MCT, the monotone convergence theorem. So we have here the limit as n goes to infinity of phi sub n times the indicator function. Again, the definition of the integral over the set E yields the following limit. And this is 0 because we know earlier this is valid for the case of non-negative simple functions. Now, for real valued integrable functions, the main idea is to, let's say, separate the real and imaginary parts, or I should say the positive and negative parts, and apply the case of non-negative measurable functions. So I will leave the details for you to write down. Okay, so you just need to consider f plus and f minus, and we know that the integral over f plus and f minus is 0 from the previous step. Now, for complex valued integrable functions, similar idea will be applied. That is, we separate the real and the imaginary parts, and apply the real case. So that's the proof of the first equation. So for non-negative measurable functions or for integrable functions, the integral over a set E having a set of measure 0 is also 0. And if you can notice here, the proof follows the construction of the Lebesgue measure or Lebesgue integral. So first you start with characteristic functions and you apply this for simple functions using linearity. You extend this to non-negative measurable functions by looking for a sequence of simple functions that increases to f, so that the application of the monotone convergence theorem is valid. For real valued integrable functions, you merely or you simply separate the positive and negative parts and apply the non-negative case. And finally, for our complex valued functions, you similarly separate the real and imaginary parts and then utilize the real case. The second statement here, so the Lebesgue integral is 0 if and only if the set where f is non-zero is also equal to 0. And the proof is analogous to what had been discussed previously. So I will now leave the details for you to read the course notes. So the ideas are the same as before. To close this section, let me state with the following theorem. And this is the absolute continuity of the Lebesgue integral. So consider a Lebesgue integrable function f. So given a positive epsilon, there exists a delta which is positive and in general depends on epsilon and on the function f, such that if A is a set, a measurable set having measure less than delta, then the integral of f over this set is less than epsilon. Well, the geometric interpretation here is that if we view the Lebesgue integral similar to the Riemann integral as the area, we can make the area sufficiently small if we make the base to be small. So again, you can think of this as your height, your set A here as your base or your width, and this part here, the integral would be your area. So if you make the width or the base small enough, then the area would be small as well. And the proof is based on the monotone convergence theorem. Again, for the sake of time, please see the course notes. So we can make the integral sufficiently small as long as the set where the integration is taken into is also small. And that's it for Lebesgue integrable functions. In the next lecture, we will discuss almost everywhere properties and the convergent theorems.